The prevailing model for planet formation, known as the nebular hypothesis or solar nebular disk model, suggests that the planets, including Earth, formed about 4.6 billion years ago. Here is a breakdown of the process. 1. Collapse of the solar nebula. The process began when a large, rotating cloud of interstellar gas and dust, the solar nebula, collapsed under its own gravity, possibly triggered by a shockwave from a nearby supernova. As the cloud collapsed, it began to spin faster due to the conservation of angular momentum, and the gravitational energy caused it to heat up. 2. Formation of the protoplanetary disk. Most of the material collected at the center, forming a hot, dense protostar, the young sun. The remaining material flattened into a spinning, disk-shaped structure known as the protoplanetary disk, orbiting the protostar. 3. Accretion, building the planets. Within this disk, particles of gas and dust began to collide and stick together, a process called accretion. Planetesimals. The small clumps grew from dust grains into boulders, then into larger bodies several miles across, called planetesimals. Protoplanets. These planetesimals continue to collide and merge, growing into even larger Moon or Mars-sized objects called protoplanets. Gravity played an increasingly important role, pulling more material onto the growing body. Differentiation. For a planet like Earth, the immense heat generated from impacts, gravitational energy, and the decay of radioactive elements caused it to partially melt. This led to differentiation, where the heavier elements like iron and nickel sank to form the core, while lighter, rockier materials rose to form the mantle and crust. 4. Rocky versus gas planets. The difference in composition between the rocky inner planets Mercury, Venus, Earth, Mars, and the gas giant outer planets Jupiter, Saturn, Uranus, Neptune is explained by the temperature gradient in the disk. Inner system hotter. Close to the young sun, temperatures were high. Only materials with high melting points, like metals and silicate rock, could condense into solids, forming the terrestrial, rocky planets. Outer system cooler. Farther out, beyond the frost line, temperatures were low enough for volatile, lighter compounds like water, methane, and ammonia ices to condense. These icy and gaseous materials added to the cores, allowing the outer planets to grow massive enough to then capture huge amounts of hydrogen and helium gas. This process of accretion and differentiation ultimately led to the planets settling into their